He's a water expert in every sense of the term and has written a number of books on water management and the coming water crisis. And Bob is going to talk to us today about the coming water crisis, I think, because his title is Come Hell and High Water, the Social, Economic, and Political Consequences of Hydrologic Change. So please join me in welcoming Bob Sandford to the podium.
Well, first, I'd like to thank you for the kind introduction, and also to say that it's a great honor to be here. I've heard about this summit, and it's widely regarded. And I must say that I'm grateful to be at a conference that recognizes and wishes to explore the tensions that exist between the economy and our life-sustaining environment. There's probably no domain in which the tension between the economy and the environment is more clear than in the way we regard and value water. And as I crisscross this country, I've discovered that putting hydroclimatic change into an economic context in Canada is rather like showing up at a knife fight with a thermometer. You know, it's logical, certainly, but not a measure your opponent will necessarily respect. So discussions leading up to this conference have inspired me to reframe my presentation. I was really grateful that Peter talked about science fiction, to reframe it around a different way of thinking about the link between hydrology and economy. And I think we continue in Canada to view water largely through the imperfect, if not short-sighted lens of our current economic thinking and practices. And my notion is, what if instead of viewing water through an economic lens, we viewed our economy through the much more transparent lens of water? And I'm going to try to do this today, and I'm going to try to use Hollywood to help me. Which you can see will probably have some problematic collisions in this discussion. But I'm sure that many of you would agree that it's not easy to set the public record straight with an accurate interpretation of the relationship between water and climate. Popular culture has gotten there first and has a very strong hold on the public imagination. And the media and entertainment industry has made a lot of money, but as you will see, has not necessarily left us well informed. In our society, we derive, as everyone in this room will know, a great deal of what we know and what we think we know, not from science directly, but from movies and television. And much of what people presume, for example, to know about dinosaurs comes from watching Jurassic Park. And one of the reasons we love science fiction so much is that it demonstrates what might be possible if only we had enough imagination. And unfortunately, finding intact 200-million-year-old DNA in amber is not as easy to do as it appeared in the movie, nor is it getting DNA out of an insect trapped in amber easy to do without contaminating it. And filling in large gaps in genetic strands with frog DNA are not likely to produce a viable genome because their constituents have not evolved together and, in effect, don't know how to talk to one another. So even if you were successful in implementing or implanting DNA into an appropriate egg medium, it would be very difficult to overcome developmental problems associated with gene splicing. And even if you're able to hatch the eggs, there would be problems with compatibility with contemporary bacterial environments. There'd also be challenges with humans replacing parents in behavioral instruction. I've thought about this. Raising teenagers is one thing, raising velociraptor is quite another. And because there were so many predators, the number of dinosaurs in Jurassic Park would have required more room than they were provided. At 20 square miles, the park on Isla Nublar was too small to provide adequate natural food supplies and prevent habitat destruction. And in fact, the dinosaurs were hungry. This fact did become evident in the film when the dinosaurs began to eat the central characters. And some of you may remember what I thought was a highly symbolic moment in the movie. I don't know how you feel, but there was something deeply satisfying about a dinosaur eating a lawyer. As a consequence of undersea volcanism caused by seafloor spreading, the concentration of carbon dioxide in the atmosphere during the Jurassic was more than 2,000 parts per million, 5 times what it is today. So predators aside, it was a much hotter world in which I will explain humans would have found it very difficult, if not impossible, to survive. A great majority of people have also learned what they know or what they think they know about climate change, not from science directly, but from popular books, movies, and made-for-television epics that interpret science in an entertaining and imaginative way. And a great deal of current public interest in climate change emerges from the highly public debate over whether or not it's actually happening, and if so, what's causing it. And while these matters have been settled in the scientific community for some time, a high-profile and very profitable denial industry has come into existence to create a market for doubt. And one of the most vocal deniers portrayed in the opening scenes of a recently released James Baylock film called Chasing Ice is a San Francisco television meteorologist named Brian Sussman. And in 2010, Sussman published a book called Climate Gate. A veteran meteorologist exposes the global warming scam. And it's widely held to be one of the most vehemently anti-climate change books ever written. And I would submit to you that while it can be very painful for anyone versed in the hydroclimatic sciences to do so, it can be highly instructive and even very useful to read such books and critically examine the arguments that they put forward. So I read Sussman's book, and I identified some 77 distinguishable arguments. And I think it's only right and fair to acknowledge the fact that despite Sussman's aggressive contrarian disposition, there were arguments put forward in this book with which I largely agreed. And all 3 are worth noting. And well, not technically a climate-related argument, I certainly agreed with Sussman's opinion of the fans of the Minnesota Vikings. I thought his opinion was good. On page 30, Sussman agrees or observes that by virtue of wearing horn hats and proclaiming that their quarterback is an ancestor of Eric the Red, these fans may be truly certifiable. Could be. I also agreed, but only partly, with Sussman's argument on page 118 that the shrinking of Lake Chad is not caused by global warming. He's only partly correct. Irrigation overdraft is a contributing factor to climate change impacts. But Sussman and I are in full agreement with respect to his argument number 39 on page 105, which makes the claim that the movie The Day After Tomorrow does not accurately portray current science knowledge or accurately represent possible future climate change scenarios. You know, I think he's right. Now, and I think the point that he makes too is that climate disaster movies have in fact caused some confusion about how the climate actually works. So what I'd like to do is take a look at some of these movies and see what they say about climate change. So let's try along the way to show where the science has been bent out of shape for the purposes of entertainment, so we can better understand what's really happening here in Canada with respect to climate change. The Day After Tomorrow was a smash hit in a growing science fiction genre that many call disaster porn. I like that. The 2004 film was made in Toronto and Montreal, and when adjusted for inflation, is the highest grossing Hollywood film ever made in Canada. And the film, if you haven't seen it, depicts catastrophic effects of global warming in a series of extreme weather events that usher in global cooling that leads to a new ice age. And after a massive drop in ocean temperatures in the North Atlantic, scientists conclude that the accelerated melt of polar ice has started to disrupt the North Atlantic current, plunging the entire northern hemisphere into deep cold. And the situation worsens when the resulting storm system develops into 3 hurricane-like superstorms. And in the eye of each of these storms, air temperatures drop to 150 degrees Celsius below zero, and everything the air touches instantly freezes. It's like Winnipeg. So this is pretty scary stuff, you know, and the question you got to ask, well, is this likely to happen? Well, not anytime soon, and certainly not at anything like the rate in which cooling was portrayed in the film. What would be required to cause the shutting down of the North Atlantic current would be a disruption in what is called the Atlantic Meridional Overturning Circulation, or AMOC as it's called, and it's sometimes referred as the Global Ocean Conveyor Belt. And it's an important component in the global atmosphere, ice, ocean, climate system, and it redistributes heat between polar and equatorial regions and among the Earth's ocean basins and the atmosphere. And it also contributes to the sequestration of anthropogenic carbon by the global ocean. Now, some of you may remember that there was genuine concern in the 1990s that the rapid melt of the world's great ice caps and ice sheets might disrupt the global ocean conveyor belt and bring about an abrupt cooling in the northern hemisphere. Recent research suggests the chances of this happening in this century, however, are low. All bets are off, however, if we continue to alter the composition of our atmosphere, in which case the science in the day after tomorrow might not appear nearly as laughable to future generations. So let's look now at movies about another phenomenon associated with the rapid melt of the world's ice caps, ice sheets, ice fields, and glaciers. And one of the truly frightening climate change scenarios is rapid and extreme sea level rise. The film that tried to scare us the most on this topic, of course, is Kevin Costner's 1995 epic Waterworld. Now, if you haven't seen this film, the setting is in the distant future, somewhere perhaps around 2500. In the beginning of the 21st century, the polar ice caps began to rapidly melt and sea level began to rise hundreds of meters, covering every continent and turning Earth into a water planet. And remaining populations were subsequently scattered across the ocean in individual isolated communities consisting of artificial islands and mostly decrepit sea vessels. And the plot of the film centers around an otherwise nameless hero, the mariner, a drifter who sails the ocean in his trimaran. So is this likely to happen? Well, not a chance. The first problem with the movie, at least in scientific terms, is that even if you melted all the ice on the planet, there wouldn't be nearly enough water to submerge the continent. So this is what North America would look like if all the ice in the world melted. Now, you really want to pay attention if you lived in California, the Caribbean, in southern Texas, Louisiana, Florida, the Carolinas, New York, Boston, or Halifax, but if this happens, everything's going to be fine in Fort McMurray. So even in the unlikely event that the West Antarctic ice sheet melts, mean sea level rise would only be in the order of meters instead of inches. It's still not the end of the world. A far more immediate climate-related threat is the potential effect of sea ice melt on ocean acidification. Because of this, the world's oceans are now 30% more acid than they were in 1800. And by 2050, our oceans are expected to be warmer and 150% more acid than they were 2 centuries ago, with cascading effects on all marine ecosystems. And also, at the same time, by mid-century, we can expect land surfaces to be warmer. So let's see now what movies have done with heat. Heat waves in themselves have not been the subject of high-profile Hollywood movies, but because they can be devastating and drive people to the limits of their physical and emotional endurance, heat waves have been the backdrop in a number of movies, including Spike Lee's Do the Right Thing. And the plot of this 1989 film develops around racial tensions that explode into a riot in an urban American neighborhood during a heat wave. And heat waves really do annually kill people by the thousands in concentrated urban areas around the world. Over 4 months in the summer of 2003, 70,000 people in 12 European cities died of heat wave-related ailments. And this problem's not going to go away. Rising levels of urban heat are now seen to constitute the single greatest climate-related threat to human health globally. Urban heat waves now account for more deaths per year globally than all other forms of extreme weather events. And we don't have to wait for the future for this. This is here. And while exacerbated by the general warming of the global atmosphere, it's important to point out that the increasing number of heat waves in cities is as much a consequence of urban design as it is of greenhouse effect. One, however, does feed the other. Because of the heat island effect of dark surface solar absorption combined with waste heat from vehicles, industry, buildings, and even people themselves, cities can be as much as 12 degrees Celsius higher in temperature than the surrounding countryside. And with what would only be a moderately warm temperature increase in surrounding areas, we discover that big cities can create their own heat waves. Heat-related deaths underscore the limitations of the human body to withstand extremes of heat, which explains probably why we wouldn't have done very well during the Jurassic. And it is true that we can, as a species, survive surprisingly high temperatures because, in part, our metabolism operates at 37 degrees Celsius, which is usually considerably warmer than most outside temperatures. Above 37 degrees Celsius, however, the body must cool itself through evaporation in the form of perspiration. And unfortunately for the very young and very old and those with health problems, the human heart has to work harder in heat wave conditions to distribute water for cooling through perspiration loss. And keeping up with this loss requires constant hydration. And this is why most of the deaths during a heat wave happen at night. When sleeping people don't hydrate, their core body temperatures rises and their organs shut down and their hearts stop. And one of the major reasons big cities are so much warmer now than in the past is the loss of trees and other vegetation to development. Trees are not only heat absorbing in their function, but they also store heat absorbing water, and their canopies create shade that moderates high temperature. So once the heat island effect is generated, it's very, very hard to reverse. And as Brian Stone points out in his book, The City in the Coming Climate, even if we cut greenhouse gases significantly, we're going to have to redesign our cities to make sure that they can allow us to be resilient in dealing with higher temperatures. What is also very interesting is that the new genre of disaster films has done a great deal to really scare us with the idea of bigger storms such as we saw in Calgary and Toronto. And I've got to point out that some of the films in this are truly scandalous, well worth watching. And there are some really outrageous ones. And hands down, the all-time worst of B movies on climate change is this film called Sharknado. Now, if you haven't seen this, the premise of this film is that climate change is going to cause more powerful storms which will result in unexpected events. So in Sharknado, the unexpected event is a massive storm off the coast of Mexico that forms a tornado at sea so powerful that it sucks 20,000 sharks up into the sky. So I think you can see where this is going, eh? So the storm, of course, hits Los Angeles in all its fury. The sharks fall out of the sky, and in the ensuing flood take over the city, attacking people in their Beverly Hills homes, occupying their swimming pools, and get this, shooting out of manhole covers to eat unsuspecting pedestrians whole. It's an interesting plot. You may want to take science in the film with a little grain of salt. In fact, it might not be a bad idea either to drink heavily before you watch that. More credible, but still widely exaggerated film on extreme weather events was a 4-hour television miniseries produced in 2005 called Category 7, The End of the World. And the premise of this riveting series is that storms of unprecedented ferocity are now not just battering, but destroying cities around the world. And while television evangelists proclaim end times, a newly charged and powerfully motivated FEMA is determined to find out what is triggering extreme disasters of a magnitude never witnessed before. And of course, with the help of renegade scientists, probably like Norm Yan or something. What happens here is, and of course working with the US Air Force, it's discovered that urban heat islands are shooting thermal columns upward into the mesosphere, creating openings down which the cold of near space is brought to the surface of the Earth, causing never before witnessed Category 7 storms. And just as this Dick Cheney figure is sucked into the whirlwind and the White House is destroyed by the superstorm, the day is saved. The solution, of course, is to shut down all the thermal power stations around Washington, D.C. But besides saving FEMA's reputation, the film Category 7, I thought, had the absolute very best line of all the disaster films I've ever seen. A renegade academic male sub-hero says the following to a very beautiful, very intelligent sub-heroine researcher: "You are an egghead, but deep down you have a redneck heart." So you can see that there's still going to be hot stuff in So the legitimate fear to which these films appeal is that we're experiencing an increase in the frequency or intensity of extreme precipitation events, including heavy rains, damaging flooding, droughts, hurricanes, and tornado. And the real interesting thing about Category 7 is that it was shot in and around Winnipeg, and that fact in itself invites us to examine what the climate disaster genre has done to scare us out of our minds with the prospect of more and bigger tornadoes. Well, Dorothy, this still looks like Kansas to me. Now, don't you just love the bewildered look on the face of that cow? Whoa, what's happening? And Twister is a 1996 disaster drama film starring heartthrob Helen Hunt and Bill Paxton as storm chasers researching tornadoes. And in the film, a team of storm chasers try to perfect a data-gathering instrument called Dorothy that's designed to be released into the funnel of a tornado during a tornado outbreak in Oklahoma. And they're of course, they're competing with the bad guys, another better funded team with a similar device. And the researchers finally get Dorothy launched, but the climax of the film is when they chain themselves to an irrigation pipe and find themselves staring up into the vortex of a Category F5 storm. It's really good, you gotta watch that. Now, so this asks us, well, where do we stand presently in terms of scientific understanding of tornadoes? And in terms of absolute tornado counts, the United States leads the list with an average of over 1,000 tornadoes recorded each year. Canada is a distant second with 100, but trends are difficult to establish. But the problem is that tornadoes are short-lived, and it's very hard to determine when they come into existence and note their presence. And so we're not clear if the intensity and frequency of tornadoes is increasing. But one thing we do know, however, is that one of only 9 Category F5 tornadoes to have occurred in North America between 1999 and 2011 touched down in Ely, Manitoba in June of 2007. Now, there wasn't loss of life, but what this reminds us of the fact is that Canada has its own tornado alley, and you're in it. And it extends across southern Ontario, picks us up again in southern Manitoba and Saskatchewan before it kind of does the twist around Edmonton. And I wish to point out, however, that tornado warnings have been extended into the mountains and as far north as the Yukon. So, all the disaster movie plots aside, what's really happening out there? And I don't think you need to be a scientist to figure out that our weather's all over the place. Rainstorms, ice storms, and snowstorms are paralyzing our transportation and electricity distribution systems. Both high and low temperature records are being broken everywhere. Cold snaps are persisting, snow is falling in places and in volumes seldom witnessed before. Flooding is occurring widely. But even with all this obvious evidence right before our very eyes, here in Canada we still find ourselves tiptoeing around the climate issue. So what can we actually say we know? Well, the first thing we know is something that we've known for thousands of years, and it is that human activities can result in climate change even in the absence of greenhouse gas emissions. Civilizations long before ours, before fossil fuels came into existence, knew the consequences of sweeping land use changes. And we now know that landscape change can have twice the impact on global warming on a micro-regional basis than average increases in global gases alone. And it's estimated that we've altered 1/2 to 1/3 of our planet's surface. And what we're learning in our time, if on top of that landscape change, on top of all these effects, you add more of certain substances that already compose it to the atmosphere, such as carbon dioxide and methane, then both landscape and climate change can accelerate. And at a certain point, they begin to feed one another, one bolstering the other. The second thing we know is that warmer temperatures are causing changes in the rate and manner in which water moves through the global hydrologic cycle. As I'll point out, simple atmospheric physics decrees that a warming atmosphere can hold more water vapor, which can serve as fuel for larger scale rainfall events of ever longer duration. And the third thing we know is that the loss of polar sea ice appears to be causing the jet stream to meander, causing destabilization of historic weather patterns, which in combination with a poleward advancement of tropical storm tracks and the atmosphere's capacity to carry more water vapor appears to be resulting in more extreme weather events. So we see that the flooding that we observed in Manitoba and Saskatchewan in 2011, in British Columbia in 2012, in Canmore, Calgary, Toronto, and Colorado in 2013, and the widespread flooding in the UK and in Europe are all linked, it appears, to hydroclimatic consequences associated with the combined effect of a warmer, more turbulent atmosphere. So, what can science tell us about all this that we're not getting from the news, from television, or from Hollywood movies? So please allow me to introduce some of the teleconnected hydroclimatic effects that researchers have identified as threats to the stability of our weather systems. So to begin, one of the most significant recent advancements in hydrometeorology is the realization of the global importance of the refrigerating influence of ice. And three factors related to the extent and duration of Arctic sea ice has emerged as having great significance to the lives of every person on this planet. And the first is the amount of heat required to melt sea ice. The second is the potential effect of sea ice melt on ocean acidification, which I've already mentioned. And the third is the critical effect. The third critical effect is the profound influence of Arctic cold on the stability of weather conditions further south and globally. So water, as many of you in this room will know because you live in a water landscape, is an almost otherworldly substance. Once it's frozen, it takes an enormous amount of heat to weaken the hydrogen bonds that hold water molecules in the fixed crystalline structure of ice. The amount of energy to require to melt 1 kilogram of ice that is already at 0 degrees Celsius is equivalent to the amount of energy required to raise the temperature of 1 kilogram of liquid water 79 degrees. And from this we see that why ice and snow are such effective refrigerants. The same thing is that the strange thing is you have to put all the heat in before there's any change whatsoever in the crystalline structure. And it's only when ice reaches 0 degrees Celsius that it melts. But water's energy absorption capacity doesn't end there. The energy required to evaporate a kilogram of liquid water would raise its temperature about 600 degrees Celsius if evaporation did not take place. This is an amazing substance. So what we see is polar sea ice is now seen as a thermostat that governs major weather patterns globally. And it's now feared that the decrease in the extent and thickness of sea ice could be a parameter that is feeding all of the increases that are causing concern over climate effects. And what we see also is that the loss of Arctic sea ice and the reduction in the extent and duration of snow cover in the northern hemisphere are reducing the temperature gradient between the pole and the tropics. And it's this difference in temperature between the polar region and the warmer air to the south that largely defines the behavior of the jet stream. And what we're seeing is that as the sea ice melts and the Arctic warms, the warmer air expands further south, the jet stream slows, becomes wavier, and weather patterns persist longer where they're at and do things that we don't expect. And much has been made in the media lately of the role of the polar vortex. Now there's actually two elliptical or circular polar vortices, one usually over the Arctic and one over the Antarctic in their respective winters. And the latter is very stable. In the Arctic, however, the vortex is more variable, and it's influenced from below by changing Arctic sea ice cover and from above by warming in the stratosphere. And this winter, both factors have served to weaken the vortex, and a weak vortex is much more susceptible to disturbance at its periphery by the polar jet stream. So instead of one consolidated vortex over the Arctic, there developed four lobes with cold circulation that carried south in troughs of the jet stream. And one of these lobes descended and lingered over eastern and central North America, which I don't believe I need to tell you. So another created rain-induced floods in the UK, but really interestingly, at the same time, Greenland, the Yukon, Canadian Arctic, and Alaska were unusually mild. Now, observations of the jet stream have revealed that warmer atmospheric temperatures don't automatically translate into warmer weather. And as we've seen this past winter, in a uniformly warmer and therefore more turbulent atmosphere, both warm and cold fronts end up and persist in places in the mid-latitudes in which they were not common in the past. And what we're seeing also, as I've mentioned, is that changes in the atmospheric circulation patterns are pushing major subtropical storms toward the poles, often causing floods of magnitudes we're poorly equipped to manage. So this is why we're seeing, and this is very interesting, we're seeing this more and more widely, especially in the central part of the country and in the west, droughts and wildfires followed by major floods in the same basins in the same year. We have farmers in Saskatchewan who have received flood insurance for the spring and drought insurance in the fall in the same basin. And this is what I'm talking about, come hell and high water, if you will, what's becoming clear is our hydrology is changing. And while we may not have perceived it as such, what's happening hydrologically in the Arctic and in the north is exactly what's happening in much of the rest of Canada. Warming is causing the post-glacial hydrologic wealth of Canada to change form. Now the water's not disappearing, water doesn't do this, but what is happening is that liquid water is moving to a different place in the hydrosphere where it may not be available for our use when we want it, as in the case of extreme drought, or where under certain circumstances it can cause a lot of damage through flooding. Dr. John Pomeroy and his colleagues at the University of Saskatchewan have observed an increase in rainfall on the Canadian prairies. What's interesting about this, though, is that most of that rainfall, or more of it, is being produced by multi-day rainfall events generated by frontal storms coming north, for example, from the Gulf of Mexico, as opposed to local thunderstorms. Everybody there is local. They're used to the big thunderstorms. It rains really hard for 3 hours and that's it. But we're seeing now these big events, and we can expect more precipitation generally in many places. That precipitation may come in fewer and more powerful storms. And this suggests a change in weather patterns that on top of already substantial existing natural variability will impact much of North America. And it's interesting to note that some people believe that despite the polar vortex anomaly this winter, warming temperatures are expected to continue to cause water left on the land after the last glaciation in the Great Lakes region to evaporate. So the question you might ask, well, where's all this water going? Well, one of the places it's going is into the atmosphere, as I said, where it's available in fuel more frequent and intense weather events. And we're seeing this right across Canada and in Europe and throughout the Northern Hemisphere. And the algorithm upon which this assertion rests is one of the most basic principles in atmospheric physics. Warmer air can hold more water. The amount of water the atmosphere can hold increases by 7% per degree Celsius, or about 4% per degree Fahrenheit. And this isn't speculation. A report published by the National Academies of Science in the United States in late 2011 confirms how serious the loss of hydrologic stationarity could be in North America and around the world if current trends persist. Now you have to think about why this matters. The problem is this: when you find that one thing depends on something else, that in turn depends on something else, what you realize is the whole series of interaction depends on constancy. And that's what our hydrologic cycle is like. Hydrologically, we have lost constancy, and now we're losing stability. So continuing to assume the past is a guide to the future is no longer practical, or as some saying, no longer even legally defensible. What this means is that some of the old math and some of the old methods of managing water will no longer work. And this is what has been at issue following the 2013 flood in Alberta. So the question you may wish to ask, well, is this something we should be worried about? I think so. And one of the reasons for that is that we're beginning to observe phenomena in the atmosphere that we didn't observe accurately before. And one of those phenomena is the phenomena of atmospheric rivers. Atmospheric rivers have likely existed for an eternity, but only now, because of satellite remote sensing capability, do we know of their existence and dynamics. These corridors of intense wind and moist air can be 400 to 500 kilometers across and thousands of kilometers long. They can carry the equivalent of 10 times the average daily discharge of the St. Lawrence River. And perhaps the best known atmospheric river in North America is what we call the Pineapple Express, which is in the top left-hand corner here. And the Pineapple Express begins as a narrow stream of hurricane-strength wind, and as it crosses the warm Pacific, that atmospheric river fills with water vapor. And we now surmise that 42 atmospheric rivers deluged California between 1997 and 2006. On one hand, supplying precious water to a very dry state, but on the other hand, causing devastating floods. And we have also been confronted recently with a frightening new realization. We have discovered that atmospheric rivers derive their energy from the temperature gradient between the poles and the tropics. And their intensity also derives from the Clausius-Clapeyron relation, in that the warmer the air, the more water atmospheric rivers can carry. Now, atmospheric rivers produce flooding of the magnitude that we saw in Australia and Pakistan in 2010, and we suspect also atmospheric rivers played a role in the flooding in the Great Plains of North America in 2011. Atmospheric river circumstances also broke rainfall records by 87% in central British Columbia in 2012. So you can bet that all of this was very much in our minds when on the evening of Wednesday, June 19th of last year, the rain began to fall where I live in Canmore, initiating the largest single natural flooding disaster in the history of Canada. But the thing that's interesting, while there was a lot of focus on that, the flooding didn't stop there. This is what downtown Toronto looked like on July 8th. And the uncertainty of a changing climate clearly demands from this, we see, a faster response. But what has been in the news about Toronto aside lately, making decisions and funding action in a municipality the size of Toronto is akin to moving mountains. And an unfit stormwater system, the crippling cost of replacing it, a host of competing political interests, all these things together presently prevent Toronto from becoming a resilient city. And there are many cities like Toronto. Unfortunately, the flooding in Alberta and in Ontario in June and July of 2013 is nothing compared to what the atmosphere is capable of delivering in the future. And this was made evident by a series of extreme weather events that happened in Russia shortly after the flooding in Canada. And we had our own problems, so we didn't pay attention to this. But what happened in Russia, it is almost beyond imagination. It is the stuff of science fiction. The weakening of the European jet stream caused a reduced snow and ice cover, which led to the creation of a heat dome, a huge high-pressure region in northern Siberia. And in July, hundreds of wildfires broke out that were so hot they melted the permafrost below the burning forests, creating methane releases from the thawing tundra that added fuel to the fires. Then in early August, in the midst of what was coming to resemble a virtual firestorm, 3 atmospheric rivers collided over the region and within 4 days created a flood that covered 1 million square kilometers. So again, we see floods and fires of a magnitude seldom experienced before in the same basin in the same year. But in this particular instance, we see something darker. It appears that we're melting the frozen lid of the jar containing the world's methane. Now, there are also concerns that the kinds of storms that we will have in the future may be fundamentally different in character than those we are used to experiencing. And at an recent international conference in Canmore, it was demonstrated that many of our recent floods were similar in many ways. Each involved rotating low-pressure systems that remained in the same place for an unusual period of time, bringing continuous precipitation up from the south, which resulted in long-duration, heavy rainfall events that covered very large areas. And while exhibiting all these characteristics, the Colorado flood of 2013 was really actually somewhat different than these others in that it occurred in September. And researchers are examining these anomalies. The behavior of these storms suggests that precipitation may have been generated by processes of raindrop formation more typical of the tropical region in which the storm originated than in local temperate conditions. And the state of Colorado climatologist Nolan Deskin noted that the storm shattered all records for the most water vapor in the atmosphere. So what we can surmise from this is the floods of 2013 offer us a glimpse into the wild weather that we might expect in a warmer world. So I'd like to conclude this presentation. I was so grateful that Peter had an image like this up in his presentation. I'd like to conclude this presentation by summarizing what we might learn from what we know about our changing hydroclimatic conditions. And what we're seeing is that the hydrologic game is clearly changing. And we are fortunately beginning to glimpse how the main rules are going to change. We know that hydrologic conditions on this planet have always been changing. We have been fortunate to have had a century or so of relative hydroclimatic stability. That era is over. The long-term hydrologic stability of the climate we experienced in the past will not return during the lifetime of anybody in this room. The game change means that simply managing water in ways that are useful to us locally are not going to be enough. We now have to be alert to changes to the larger global hydrologic cycle, and where possible, understand them, manage, and adapt to them. And this is a huge new concept, and I would submit to you that ultimately this will affect every sector of our economy. Second thing is that what we have seen is what we're going to get. Predicted rises in temperatures between 2 and 6 degrees Celsius would result in further amplification of the hydrologic cycle by 15 to 40% or more. And this game change is not going to go away. And the new normal, I regret, as all of you probably have said to one another already, well, is that there is no new normal. And unless we want our future to continue to be a moving target, sooner or later we're going to have to confront the fact that we're rapidly changing the character of the surface of our planet and at the same time altering the composition of its atmosphere. And that's a subject I would submit to you that no one wants to talk in meaningful terms, at least where I live in Alberta. So what has become clear is that it's not just emission cuts that we need to achieve to restore relative climatic stability. Difficult as these cuts may be, they're not going to be enough. In order to adapt and flourish, we have to set new ecological restoration goals as well. And this suggests that structural engineering solutions to these problems will not in themselves save us. Sooner or later, a storm is going to come along that will overwhelm the most expensive engineering works that we can afford. And this means that sooner or later, we may have to move out of some of the most vulnerable floodplains. In this context, however, it's important to note that the watershed basin is the minimum unit at which water must be managed. And this fact in itself, the fact that basin-scale water management is critical to social, economic, and environmental resilience to changing hydroclimatic conditions throughout this country should inspire our actions, as did that opening film. And I think now, while the memory of recent flooding is still fresh and before the next disaster, I think it's really time to press for this. And I also want to end somewhat realistically, but optimistically, by saying this is not the time to throw up our hands in hopeless despair. We are not helpless, and as we'll discover in the next 2 days, we're hardly without a means to deal with this. Just like in the movies, this is a time instead for courageous and relentless citizenship and true, inspired, heroic leadership. The problems hydroclimatic change is bringing in its wake are not going to go away. And whether we like it or not, the filming is already started. And we should not expect a Hollywood ending. Wishful thinking and last-minute heroics are not going to get us out of this, but good science, thoughtful, and timely local action will, if our economy permits us to do so. I remain hopeful. And I'm betting that the movies future generations make about us are going to be worth watching, because I, for one, am counting on the people in this room to save the day. I'm counting on you to be stars. Thank you very much.